All right, so today, guys, we are going to be looking at what happens when two or more waves try to occupy the same space at the same time. This is something waves can do, but matter can't. Okay? When two objects with mass try to occupy the same space at the same time, that's not generally very good. Okay? They smash into each other, they have mass and volume, that can't happen. But with waves, because they're energy, they can absolutely occupy the same space in the medium they're traveling in at the same time because they are energy. The thing that comes into play for this, though, is what does the medium have to do to show how much energy from those two or more waves? Okay, how does it show that? How does it reflect that there is X amount of energy in that particular spot at that particular time? Okay, so we call that interference. There are basically two kinds. There's constructive interference, okay, and there's destructive interference. Now, constructive interference means that the amplitude of the waves gets bigger. Okay? That would mean that they have to be what we call in phase with each other. Okay? So if one wave is a crest, the other wave is also a crest at that time, and the amplitude of the medium would go up. Okay? But if I've got a crest and a trough, and they try to occupy the same space, they're going to cancel each other. Right? The shape the medium would take to represent how much energy is in that spot, if they were like an amplitude of +1 and -1, would be flat. It'd be 0. Okay? So the two kinds of interference basically result in different changes in shape to the medium. But it's a simple rule. The simple rule is if you want to know what the amplitude of the medium will be, you add the amplitudes of the two waves. Okay? When it comes right down to it, that is what we call the principle of linear superposition. Okay? What's the amplitude of the medium going to be? It's the amplitude of the two waves. Add them together. Okay? If one's negative, it'll work out. Everybody with me there? Okay. Anybody in here have active noise canceling headphones? Okay. Do you know how they work? Alex?
They have microphones on the outside and then speakers on the inside, and it listens in and sends out the reverse polarity wave, which cancels them out.
Exactly. They use the principle of linear superposition. Active noise canceling involves having a microphone or a receiver of some kind on the outside of the headphone that is detecting the ambient noise. Okay? The headphones themselves are playing your music, your podcast, whatever it is you're listening to, okay? And waves that will counteract the waves it detects on the outside of the headphone. Okay? The technology was originally not meant to be, was not designed for headphones, like to improve the quality of the sound you hear. It was actually designed as hearing protection for people who worked in very loud areas. In particular, the technicians and people that work on on the ground at an airport. Okay? Jet engines are incredibly loud. Right? And so they would have these active noise canceling headphones that would simply emit sounds that were the opposite of what the jets were doing, and it would protect their hearing. They would wear the big earmuff style ear protection. Okay? So active noise cancellation simply involves having a little computer processor in those headphones that is detecting waves and producing the opposite in order to actively cancel, okay, the ambient sounds in the area. And unfortunately, the technology works very well, okay, as evidenced by any parent who's trying to get their kids' attention while they're wearing them. It doesn't matter how hard or how loud you yell and how far away they are, they don't hear anything. It's really frustrating, okay? But that's a me problem, okay? So that's how they work, though. Okay, they're just using the thing we're going to learn about today. Now, lots of musical instruments also use this, but they use the constructive kind of interference. Okay, any musical instrument that's acoustic is using resonance to create constructive interference and a greater amplitude of sound than is actually produced by the instrument itself. Okay, a prime example is an acoustic guitar versus an electric guitar. Okay? If you don't plug in an electric guitar and you strum the strings, does it make very much noise? Like you can barely hear it. Okay? You do the same thing on an acoustic guitar and it makes a fairly loud sound. Okay? On an acoustic guitar, those waves travel into the resonance cavity. Okay? They bounce around in there and they're channeled by the shape of the guitar, of the resonance chamber, okay? In such a way that when they come out, they have a higher amplitude and they sound louder. They don't just sound louder, they are. Okay? Because they've been allowed to resonate inside of there and have constructive interference. Okay? Does that sort of make sense? Okay. What about a muffler? Okay, so you got a muffler on your car. Maybe you don't. Maybe you're like that other guy in my neighborhood who doesn't know what mufflers are for. But if you have a muffler on your car, it makes your car quieter. Okay, it's doing the same thing. It's just trying to make it so that the waves, the sound waves produced by your car's engine, which are really loud, okay, bounce around inside the muffler, okay, and are deadened essentially, okay, or canceled out by themselves, okay, in order to make the car sound less, okay, quieter. Okay. So, if we're looking at constructive versus destructive interference, this is essentially what we're looking at. Okay? In constructive interference, okay, the amplitude of the waves is not. The struggle is real today. Destructive. There we go. Okay, interference. The waves are coming in and they are both up, or they both have a positive amplitude when they're coming in. They match. Okay? So when they come in together, okay, when they meet, if this one had an amplitude of +1 and this one had an amplitude of +1, then the resulting shape of the medium has to have an amplitude of +2. It's a simple concept. Okay? You just add the two amplitudes together and you've got your resulting shape, okay, of your medium. Right? Now, here's the thing that people don't often think about. Is that the end of it? Like if two cars try and occupy the same space at the same time, that's where it stops. Does it stop there for waves? Do the waves reflect off of each other or pass through each other? They pass through each other. Okay? They just go right on their merry way just like they were before. Okay? Remember, their energy. Okay? They just occupied the same space at the same time. They made the medium represent how much energy they had, and then they just kept going. Right? So the point after this is, here's wave B. That's the one that started out on the right. Here's wave A. It's the one that started out on the left. They've passed right through each other, and off they go. Okay? Interference doesn't permanently destroy a wave. It destroys it at the location. That's why noise-canceling headphones can work. The location is always your ear. Okay? You can always make sure that that point of destructive interference is there. Okay? It's much more difficult to do that over a wide space because you have to be canceling waves in a huge volume of air. Okay? Now, for destructive interference, okay, the other kind, it's just the opposite. All right, so I've got a wave with an amplitude of +1, a wave with an amplitude of -1. Okay? When they come together, they're still there. The wave energy is still there, but for that instant, it's canceled. Okay? And then they move about their merry way, just like the others. Okay? Waves are not permanently destroyed by each other. Okay? All right, now, we did a little video of this and slowed it down, so I'm going to show you here. Actually, I think that'll just go right to it. If I click on the clicker.
1, 2, 3.
You can actually see the reflections do the same thing after it reflects off either end and then hits each other in the middle again. I think I do the other way here in just a second. This was also the last day before Christmas. Or maybe I don't. Boy, super slow-mo takes a really long time when you're waiting for it, doesn't it? Here we go. Okay, so now we're going to get constructive because we both went out to the left.
Whoa.
Okay, so you can see, I mean, it happens exactly as the diagram says it should. Okay, those waves just pass into each other, they double up, and then they go on their way, or they cancel out and then just go on their way. Okay, pretty straightforward thing. It does have some applications that are a little less straightforward, okay, but we'll look at those probably not today, but in the future here shortly. Okay, so that's what we saw there. Okay, this one here, this is what kind of interference on the left? Constructive on the right? Destructive. Okay, make sure you say destructive. I have a lot of people who write deconstructive. Okay, that's something totally different. Okay, so we've got always though that the principle of linear superposition is that the sum of the shapes of the individual pulses is going to be what the shape of the medium is. Okay, everybody all right with that? Okay, so if you see the opposite pulses, then you get destructive interference. Okay, we've already talked about that. Okay, so predicted shape for this one, when these occupy this spot in the middle, right, be twice as big. Okay, this one here, that would be 0. Okay, so guys, this is how I'm going to ask this on a test. And sometimes this is even like a written response question. I ask you to draw a diagram. Okay, before, during, and after either constructive or destructive interference. Okay, if I ask you to do that and I say constructive, okay, I'm going to want diagram A to look like this. Okay, indicate which direction these waves are traveling. Okay, diagram B would be the during, and then diagram C would be the after. Okay? Simple thing, but sometimes I make that a written response question because it's hard to have multiple choice on that. I'll actually want you to draw it. Okay. All right, now very rarely is this interference like one wave. Okay, it's often a wave train or even a jumble of a whole bunch of different waves. That's typically what we associate with the term interference, is a whole bunch of waves are in the same place at the same time and they're messing with the operation of something we're using. All right? Way back in the day, I say way back, you guys were probably about 4 or 5 years old. Okay, Wi-Fi didn't have the same transmission power it has now. Okay, Wi-Fi was really more like Bluetooth. Okay, that's not that long ago. Have you ever noticed that Bluetooth is affected by your microwave? Okay, if you've got wireless headphones, okay, go into your kitchen, put your phone a little ways away, and then put your microwave between you and the phone. Fire up the microwave. I guarantee you're going to lose the signal on, if it's Bluetooth, to your headphones. It'll crackle and go, okay, because a microwave is on a similar wavelength and frequency to what Bluetooth uses to transmit information.
Wouldn't the grade stop the Bluetooth waves from getting to the door?
It doesn't.
Not all of them.
Not all of them. Yeah, and enough of them that you'll notice it. Okay, and I bring this up because it used to be worse. I had one day, it was first round of the NC2A basketball tournament, so there's a whole bunch of games going on, right? And I've got like a TV and a laptop and a tablet and a bunch of things all kind of watching, and it's crunch time. My Spartans are playing, it's crunch time there, and watching a few other games. Okay, and all of a sudden one of my kids comes in, they're hungry, and they throw something in the microwave, and only the TV was continuing to run because it was on a cable. Everything else I was running off the Wi-Fi. Okay, and of course, what the most important game was one of the ones that was on the Wi-Fi, and they were just going up for the game-winning shot, and I'm like, "Oh my God, turn that off!" And my poor hungry kid, and that was Father of the Year moment there. Okay, so yeah, they didn't see it because once those waves got in there, they just created this massive interference pattern that resulted in the processor not being able to determine what was going on anymore. The waves coming in were a jumbled mess, instead of something coherent that it could understand. Okay, as soon as the microwave turned off, boom, it comes right back. Okay, that interference is only in that particular location. It's why sometimes if you've got bad reception in one spot, you only have to do like this, and suddenly it's gone. Okay, if you get to the right spot, you might even have it a little bit better in that spot because you just happen to be in a place where it's constructive versus destructive. Okay, in fact, when people who install home theater are setting up someone's, like if they're getting a high-end home theater system, they'll actually make it so that the seating positions are generally where the sounds you would experience most often are going to constructively interfere. Okay, it's called passive amplification. All right, so in this situation here, okay, these two waves, wave A and wave B, are they in phase? In phase means when one is up, the other is up. Those are in phase. They may not have the same amplitude. Wave A has a greater amplitude than wave B, but when wave A is up, so is wave B. Okay? If waves are in phase, you get what kind of interference? You get constructive interference because they're going to line up. Okay? In this situation, wave A and wave C are completely out of phase, and that's going to result in destructive interference, because when this meets that, okay, they're going to cancel. Now, it's not going to completely cancel because the amplitude of wave C isn't as great as wave A, but I'm going to get a greatly diminished waveform because of destructive interference.
With the sound, is like something being sharp and flat, like compared to the amplitude of it, or?
Sharp and flat, I believe, has to do with pitch.
Okay.
Amplitude is volume.
Okay.
So if something has a greater amplitude, it has a greater volume. The pitch you determine has to do with the frequency.
Okay.
Yeah. So, not understanding music all that well, I understand that sharp and flat sound different, right? Are they the same, like it's F sharp and F flat? Like are they in terms of pitch similar, or the one's a flat sound and one's a sharp? I don't know how that works.
Flat is like you have a note and you bring it down in pitch.
Oh, okay.
Sorry, I'm
No, that's okay. So it is a change in
Sharp
pitch.
is bringing it up in pitch.
Like while it's being played?
No, like that's what it says. How you create different notes. Kind of.
Okay, so a sharp and a flat is different. It's the same note, but it's just changed slightly. Like not enough to go from F to G.
Yeah, exactly. So like F sharp is between F and G.
Okay.
So it's kind of in the middle. Yeah.
I understand now. Okay, that makes perfect sense. And then flat would be the other direction. I don't know what comes before F. I was just lucky on the G. Is it E?
But if there's F flat is it's whole.
Okay. Yeah. Well, that makes sense then. So it is a change in pitch. It is a change in frequency. Yeah. I don't know how they must just change the wire, or just slightly different length of wire in a piano, or yeah.
Yeah, in the pianos and string instruments, it has to do with how tight the string is.
Okay. Yeah.
But in other instruments, there are different ways to do it.
Right. Okay. So you'd have for F sharp, you'd have the same length of string, but you'd have a greater or less tension in it.
Yeah.
Okay, that makes good sense. That's good. Now I know how that works. Okay. I didn't know how that worked before. Okay. So does this make sense here? The constructive and destructive interference. Okay. All right. So here's what this can look like in a practical sense. Okay. If I had a room that was, perfectly insulated for sound, we would call it an anechoic chamber. Okay. An anechoic chamber looks really weird. Like having been in one, it looks like you're inside a meat grinder. Okay, it's got a lot of like weird edges and shapes and stuff because these walls are not anechoic. My sound waves bounce off of the walls and come back to me. It's why you sound different recorded than you do in your own head. Okay, has anyone ever noticed that? I noticed that because I record myself all the time and I'm like, you poor people have to listen to me all the time and that's what I sound like. Okay, but the reason I hear it differently is because my voice is reflecting off of other things, and so I hear it differently than you do. In an anechoic chamber, those echoes, those reflections don't happen, so you get a much truer sound. If I set up something like this, where I had two speakers placed a certain distance apart, and they were just playing a tone, so one note, I could walk around that room, and there would be places where it would be loud, and if I took a step to the right, it would be quiet. Okay? Because there'd be places where the waves would be meeting crest to crest, and there'd be places where the waves were meeting crest to trough. Okay, and I'd actually be able to just move about the room and hear all of these different levels.
You can recreate that with an ultrasonic speaker, which just shoots out like a beam of sound. It's really neat.
Yeah, well, it's actually similar to the experiment that Young's used to prove that light was a wave. Okay, so Young's, when he was trying to prove light was a wave and not a particle, had what we called the double slit experiment. So he had a single slit that light traveled through, and then after that he had a barrier that had two slits in it. Okay, and he said if light's a wave, it'll be able to diffract through these slits, travel to the next two slits, and then when it comes out, I'll get an interference pattern of light that's similar to what I was talking about here, an area where I don't hear anything. I step to the left, I hear a loud sound. But he was going to do it with light. And he was going to project it up on a screen and get like a zebra pattern of destructive and constructive interference of light. Okay? Most people who were in the particle realm looked at him and went, that is the dumbest experiment ever. Light is a particle. If you have a board with a tiny slit in it, and then another board with the slits in different places, your experiment ends right here when the light hits this board. You're so dumb, okay? Because that's been everyone's experience, right? If you've got if the hallway is dark and I open the door, a beam of light goes out through the door, right? People are like, light doesn't diffract. Diffract, what he said is, because waves diffract, when the light goes through here, it'll do this, and then when the waves hit this slit, they'll do this. And anywhere where they meet crest to crest, it'll be bright, and anywhere they meet crest to trough, it'll be dark. And they all thought, that's so dumb. You know what happens when light goes through a narrow opening, it makes a beam. Okay? And so they thought he was going to just make a fool of himself, and then he ended up pulling a Kepler, okay, and making a fool out of everybody else, okay, including Newton, who thought light was a particle. Okay? So yeah, it was kind of a big deal in terms of an experiment. Okay? So if I had this pattern here, so I've got light blue waves coming from speaker A and dark blue waves coming from speaker B, okay? Right here. Loud sound or quiet sound? Loud. If the lines are representing crests, that's an area of constructive interference. Okay? What about right here? That'll be destructive. I'm on a crest from speaker A, but I'm halfway between two crests for speaker B. What's halfway between two crests? A trough, right? A crest and a trough are always exactly half a wavelength apart, okay? I'm exactly half a wavelength from these two crests. This would be destructive. Oh, we're gonna be that way, are we? Oh, geez. Come on. Oh, it closed the whole thing. Now it's back. How weird. Okay, so this here would be destructive. Merry Christmas to you too. Okay. What a grinchy smart board.
Does this thing not respond on the top
Not anymore.
line? Oh, there you go.
Okay. Oh, there. See, I got like 3 Ds now. Okay, and that's constructive there. Okay. What about right here?
That would just be constructive.
That would be constructive. Those would be meeting trough to trough. I'm exactly halfway between crests on both the light and the dark blue lines. Okay, that would be trough to trough. That's still constructive interference. They're meeting in phase there, so I would hear a loud sound. Okay, so if I'm standing right here, okay, equidistant between these two speakers, the sound from this speaker is going to travel 1, 2, 3 wavelengths and arrive at a crest. Okay, and then this one, because it's the same distance away and emitting the same tone, it has the same wavelength. So it's going to travel 3 wavelengths, and I'm going to be standing at a spot where I always hear a sound that's louder. Everybody all right with that? Now, what if I change it so that I'm still 3 wavelengths away from the speaker on the right, but I'm 3.5 wavelengths away from the speaker on the left? Then what? Will I meet crest to crest or crest to trough? Crest to trough. Because I'm still 3 wavelengths from this speaker, I'm going to get a crest from there. But if I'm 3.5 wavelengths from this speaker, I'm getting a trough from this one. What if I was 4 wavelengths away from this speaker and 3 from there. That'd be crest to crest again. These ones would travel an extra wavelength, but they'd still be in phase. Okay, they'd still be a crest. Everyone kind of follow there? Okay, because you're almost never equidistant from 2 speakers, but you can still find spots where they're meeting crest to crest, as long as they travel a full number of wavelengths. Okay, so if from one speaker it's 5.5 wavelengths, and the other speaker it's 20.5 wavelengths, they're still meeting at that half. Okay, it's still 5.5 to 20.5. They're still meeting trough to trough. But if I'm going from one speaker and it's 2.5, and the other speaker it's 10, well, 10 wavelengths makes a crest, 2.5 makes a trough. That I would hear a quiet sound. Okay, everyone all right with that? So whether you hear a loud sound or a quiet sound is based on whether you're standing in a spot where you have a trough and a crest, or a crest and a crest, or a trough and a trough meeting. And that's determined by the number of wavelengths different in travel. All right, I'm going to show you because I got a video, actually found a video of a guy doing just that. Interference patterns, okay, basically show us all of those little details and things there. Okay, so this is what I was talking about before. Okay, if I wanted to get destructive interference, then I simply have to move to a position where I'm a whole number of wavelengths from one source, but I'm a 0.5 wavelength away from the other. Okay, that could be 0.5 wavelengths, it could be 1.5, 10.5, as long as I'm a full number of wavelengths from one and whatever I have from the other is a 0.5. Then I'm always going to be meeting, the waves are always going to be meeting half a wavelength apart. Half a wavelength apart is crest to trough. Is everyone okay with that? That's what determines whether that spot has constructive and that spot has destructive. Okay, so this is kind of what I was talking about. If you were designing like seating in a spot where you wanted to have really good sound, you try and maximize the points of constructive interference. Sometimes that can even be done electronically. With a receiver, you can make delays for certain wavelengths of sound so that they're emitted a little late and then they are arriving in phase at that position. It's not something you'd ever be able to detect, but you would get the better interference, the constructive interference at the seating position. Okay, all right, so we're going to end off with this example here. So I want you to copy this example down. I always put a question just like this on the unit exam as an interference question. Okay, so I'm going to give you a minute to get it written down and then we'll walk through how to solve it. Okay, so as an interference problem, okay, what determines whether the observer positioned there hears a loud sound or a quiet sound is the number of wavelengths the sound has to travel from its source, the speakers, to him. Okay? So if it's the number of wavelengths that determines whether he hears loud or quiet, what do I probably need to know about the sound? I'll say that again. If it's the number of wavelengths traveled that determines whether he hears a loud or quiet sound, what property of a wave do I need to know about these sound waves? The wavelength. Okay? If I know how long the waves are, then I can determine how many wavelengths there are from the source to him. All right? The question tells me, okay, the frequency of the sound, 214 hertz, and they tell me the speed of sound. So I am given in this question V, okay, 343 meters per second, and I'm given F, 214 hertz. All right, so I've got both of those things. That means I can calculate wavelength. So very simply, I'm just going to go V over F. Okay, I think it comes out to 1.6, right? Is it 1.6? Okay, so it comes out to 1.6 meters. So every wave produced by these speakers has a wavelength of 1.6 meters. All right, I know he's 2.4 meters from the first speaker. How will I figure out how many wavelengths that is?
Just take 2.4 and divide by 1.6.
Right, just take 2.4 divided by 1.6. That will tell me how many wavelengths there are. It's 1.5. Okay, so that means that from this speaker, there would be 1.5 wavelengths. Okay? So I'd see 2 crests and 1 trough. Now, what do I need to know about this distance? I kind of spoiled that. I need to know the distance. Yeah, I need to know how far that is. That's just a Pythagorean theorem calculation. Okay, so to get this distance, which we'll just call C, okay, C will be 2.4 squared plus 3.2 squared. Okay, I think it comes up to 4, doesn't it?
Mm-hmm.
Okay, so this is 4.0 meters. Okay, do I do the same thing that I did with the other one? Do I take 4 and divide it by the wavelength? Okay, it comes out to 2.5, right? Okay, so there's 2.5 wavelengths here. So there's 1 wavelength, there's 2 wavelengths, and a half. Are they arriving in phase? Looks to me like they're arriving at the same point in the wave, right? There's a crest just coming in to that person from both speakers. Okay, how can I prove that mathematically without having to draw it like that? Well, pretty easily. This was 1.5 wavelengths. This was 2.5 wavelengths. What determines whether I hear a loud or quiet sound is the difference in the number of wavelengths. If it's a whole number, then they're arriving at the same point in the wave, because a crest and a trough are always a whole wavelength apart. Or sorry, a crest and a crest are always a whole wavelength apart. Okay? If it's a half a wavelength out, then I've got a crest on one side and a trough on the other. 2.5 minus 1.5 is 1. That's a whole number. That's why they're arriving at the same point in the wave. The sound has to travel further from this speaker, but it's a full wavelength further. So it still arrives at the same point in the wave, thus constructed. Okay? So what I would want to see on a question like this is not necessarily that you drew those waves on there, but that you figured out the number of wavelengths for each one, okay, and then subtracted them. There you go, 2.5 minus 1.5 equals 1 wavelength. Okay, well, 1 wavelength means they're arriving at the same point in the wave. If they were 1.5 wavelengths different, then they're arriving at the opposite. Okay, so the final answer to this one would be they hear a loud sound. It's constructive interference. Okay? Everybody all right with that? Okay. So that's interference. That's all I wanted to cover today was the interference stuff. When we come back from Christmas, we're going to talk about wave behaviors. At a boundary, okay, just wave behaviors in general. Then we're going to move on to the Doppler effect. And then we're done. Okay? Doppler effect is the last thing that we will do. Yep. Well, this stuff can be confusing until you do a few of them.
I feel like, so, I don't even know, like, I'm a bagpiper,
Okay.
and I'm thinking about how this would be applied into tuning, because like,
Well, the pipes in your bagpipe are all different lengths, right?
so like, there's the drums, right, which is probably referring to, but they are all supposed to tune to like A or whatever, but there's different octaves.
Okay.
Just like the long one, just the bass,
Right.
there's 2 tenors.
Yeah.
And you want to tune it to like the chanter, right? You want to tune it to A on the chanter.
Right.
And I'm thinking like, so I'm pretty sure hertz maybe
Yep.
is how like the A, B, C, D, E, F, G.
Right. And you've got little holes on each one like a flute, right? Okay.
But like, there's ranges, and so there's no octaves in the pipes, which is so nice. Oh my goodness, it's actually so good. But so I'm pretty sure the way music works, it's like A, B, C, D, E, F, G, A, B, C, D, E, F, G. That's hertz.
Yep.
And then between the A's is like flat sharps, right?
Yep.
So A flat, A sharp, B flat, That's what I'm thinking. I don't know.
That's what I understood.
That's what I understand.
Gigi telling me
Yeah.
today, yeah.
And it's like, you want to it's so weird because you want to do drones so that they're making like the same sound almost. Otherwise it's like, oh, wow, it's like not good.
Okay.
And you like change the length of the drones to sharp wind and fine.
Right. So with any wind instrument, and a bagpipe is really just a wind instrument.
Yeah.
Okay. What you do is you change the length of the column of air that is resonating.
Yeah.
When we talk about standing waves, it'll make more sense. But
Yeah.
all wind instruments, in fact, all instruments of every kind, use vibrating or resonating columns of air to produce musical notes.
Yeah.
By making it longer, you're increasing the wavelength that can be produced. So it'll make a lower frequency sound.
Wavelength or lambda. If you want to get frequency, wavelength. So increasing.
You'd have this, right? You'd have, so you'd have F equals V over lambda, right? So if you make the two longer, you're increasing this, okay? This number always stays the same, because it's the air temperature you're dealing with.
So if you increase it, would it flatten out?
It could.
If it, I think decreasing frequency might flatten it. That's what I'm getting.
That would seem to, that would make sense, yeah. Then by dividing by a bigger number, you would decrease this. This number is fixed based on the temperature of the air playing.
Exactly. Yeah, so that's also, I understand that now. But so also the moisture, which is another thing, that'd be different medium, right?
Yep, yeah, humidity can change it.
Exactly. So humidity, there's all these factors. So like sometimes like you tune it in one room, then you walk to the next room, it's all whack.
Yep, I believe that.
Yeah.
Yeah.
But I'm also trying to learn how to tune it still because it's like,
It sounds like it's pretty technical.
hearing it, oh, it's super technical. Because you have to, first off, keep constant pressure on the bay.
Yeah, because if you force it through,
Like it's the different amount of, I guess, medium. You change the medium or
Pressure.
Pressure, yeah. But so you want to keep that fixed, and then you want to have the ear for the chanter to get the same. I feel like frequency has like different ranges or whatever. Or like is it A, B, C, D, E, F, G, right?
those are all different
But these
frequencies.
octaves.
Yeah,
So
it's the next, so there's different kinds of resonance, right? Like if I'm playing C in one octave, C might only have a resonating column this long, so the wave inside would look like this,
yeah, and
right? The next octave of C has to have a longer column because I'm going to have a longer, I didn't draw that very well, but I'm going to have a longer wave.
Yeah.
Same form, but it's longer. Like this wavelength only goes from here to here. That's one wavelength. Well, here to here is also one wavelength, but it's longer, right? So this would be the higher octave, and this would be the lower.
But if it's C, like let's say it's like one note, right? Wouldn't it have like something equal because then they can match or whatever?
We call them like we have the fundamental frequency, and then we have like the second harmonic, third harmonic, fourth harmonic. The harmonics are the next octave of that note.
Oh, okay.
Yeah.
So, and then you just want to figure out the hertz rate. Like that's why there's like extra tuners. It's like, oh, here's when you should tune it to, and then you just.
That's why, like on a pipe organ,
Yeah.
right, or on a flute, right?
Imagine tuning that.
Oh, well, they can slide the.
I know, but it'd still be so much worse to tune.
Oh, I would think so.
Yeah. It's like what you do, you like, you have the 3 drums, low, you can like tap it so that it doesn't get, like it doesn't make sound, and then you can tune one to it, and then you have the next one, you tune the drones to the drones, and it's complicated, but
That's complicated.
yeah. I just need, I think if once I get the ear for it, and I know what I'm tuning to, it'll be so much easier. But it's now like I'm like understanding the process
Physics of it?
Yeah.
Yeah.
It's cool.
So like I'm a person who doesn't understand the music. I don't know, but I can say, okay, well I know what's going on with the waves inside.
Yeah.
How do you make it sound good? I don't know.
I'm trying to figure that out too.
Yeah. That's the trick. That's the part that requires an ear and an artistic, ability or temperament or whatever.
It's just so
I
cool.
don't have.
But yeah, thank you so much.
You're very welcome. Have a Merry Christmas.
Yeah, you too. Merry Christmas.